In this video, I want to continue to solve differential equations using Laplace transforms, but now I want to include a new wrinkle that we haven't seen before, and that is discontinuous functions. For the most part, in the context that we're going to see these things, the discontinuous functions are going to show up as a forcing term in the differential equation. So let me start with what these functions themselves are going to look like. We're going to be concerned with basically two different functions. The first one is called the Heaviside function. So we'll encounter two discontinuous functions that we care about. Okay, so the first one is called the Heaviside function. And the Heaviside function is basically like an on-off switch. The Heaviside function, the notation that we'll use for this is either going to be a lowercase u or a capital U. Different books use different things. Ours uses a lowercase u, but in my homework solutions, I use a capital U, so it's going to be either u of t or capital U of t. And these are defined to basically be equal to two things, 0 or 1. And they're basically defined in such a way that there's 0 for all t less than 0, and then 1 for all t greater than or equal to 0. So if you were to graph this function, basically what it would look like, here's my axes here. So here's my t-axis, and here is whatever, my f of t. The graph itself follows along the negative t-axis, goes to this point but doesn't include it, then jumps up to a height of 1 and continues on from there in this manner. So that height right there would be a height of 1. So this is the discontinuous function, and we're going to use it again in a role of an on-off switch, where maybe the forcing term is turned off up until time 0, and then we'll flip the switch and have it turn on. But we're not always going to use, we're going to want to have the freedom to switch the time that we turn this on. So we don't always want to have to turn this on at t equals 0. So alternatively, we'll use basically a shifted version of this. So, or more generally, I should say, maybe that's better than alternatively. More generally, we can write the following. So if I do this notation, what I want to think about it is it's basically a Heaviside function that is turned on at time c, or basically shifting our value of time here. You can see there's a time shift built into this. So these two things are equivalent. Again, lowercase or uppercase u, both are used very frequently. And the idea is, if we think about this, this one, if you think about the argument that's getting plugged in, for values of t that are less than c, so whenever t is less than c, this argument's going to be negative, and we're on this part of the graph. But the second that we get to t equals c, that's going to make the argument be equal to 0, and that's when it will jump up and turn on, and then it will remain on for all values of t greater than c. So this one is basically an equivalent thing, and again, or we could see this written as a capital U sub c of t. And these two notations are equivalent. You'll see either the time being indicated down here that it turns on, but that's equivalent to just shifting the value of t here. So these two notations are equivalent. They mean the same thing. This just means it's a Heaviside function that gets turned on at time c. This is a mathematical way of thinking about that exact same thing. It's a Heaviside function. Remember, it's always turned on when the argument is 0, but the argument's going to be 0 when t is equal to c. So either of these notations and what they're equivalent to is now, again, 0 or 1, but they're now 0 for all t less than c and 1 for all t greater than or equal to c. And so this is going to be something, again, that we use as sort of an on-off switch. So think of this as an on-off switch for our forcing term. Okay, so that's one of our two functions, the Heaviside function, off and then on. The second function that we're going to encounter is called the Dirac delta function. So our second one is the Dirac delta function. And the notation that we are going to use for the Dirac delta function is a delta symbol that looks like this. This is the a notation that we use for the Greek letter delta, a lowercase version of it, and it has something very similar. We can write it as delta of t. And this has an interesting property that I'll kind of write out like this. So this has, again, only two values, so to speak. It's 0 whenever t is not equal to 0. And it's basically infinity when t is equal to 0, but it's a very specific infinity. So we need to be a little bit more careful than this. The delta function is kind of a weird thing, and it's actually usually defined in the context of a limit. Usually, we define delta of t in the following way. Using the limit. The idea is basically that we want to set up our graph. So in this case, you can think of the graph here. Let me just sneak it in over here real quickly. Right. Here's t. The graph looks like this. It looks like this. And then right at 0, it suddenly basically just spikes up. You can think of it as a spike, but this spike is infinitely high up. We actually define it using a limit in kind of a similar way. You can think of basically saying the following. What if we took a picture that looked like this? So here's our graph. So here's t, here's our f, the height, f of t, and I want to define it like this. I want it to go maybe in this shape. This will be fine. We'll do it like this. I want it to look like this shape. This is our function. So we're coming in on here, and then it basically jumps straight up. So if you want to think about the sides that I drew in, maybe I shouldn't have drawn them in as solid lines. You can think of them as basically dotted lines. And back down to here, and it continues on indefinitely in that direction. But we do it in such a way that basically I want to make this point right here be a half, this point right here be negative a half, and the height here should be 1. So this is what our starting point kind of looks like. And if we were to integrate through this function, we would find that the area under the curve, well, in this case, we can determine that geometrically, right? It's just going to be a rectangle. And in this case, it's actually even a square. The width goes from negative 1/2 to positive 1/2, so that's a distance of 1, and the height is also 1. So if I integrate through this function that I've drawn right here, which isn't the delta function, but it's something that we're going to use to define the delta function. If I were to integrate through this function, we'd find that the area under this curve is 1. It would integrate to 1. So if I integrated from negative infinity to positive infinity, it's 0 everywhere. It's not contributing anything to the area except for right in this one little region where the area is 1. And what I want to do is I want to start to squeeze in the width of this thing while preserving the fact that I want it to integrate to 1. And to make that happen, as I squeeze it inward, we're going to have to raise the height of it upward. So basically, we would take the next picture would look like this. So we're going off to t. Again, here's our f. The next time, I need it to go up to be this shape. So it continues on over here, it goes back, oops, indefinitely to the left. But now this is -1/4, +1/4, and the height here is 1, and the height up here is a height of 2. And so now the width of my rectangle is only a half, the height is 2, and we've preserved the area to be 1. And what I want to do is basically take the limit as these two pieces go to 0. So I want to shrink these 2 points where we break upward. I want to shrink them towards 0 while simultaneously raising the height of this thing enough to preserve the fact that the area under this is going to be basically 1. So in a sense, if you think about sort of the width and the height, in the first one we looked at, the width was 1, the height was 1, and that gave us an area of 1. And the next one, the width was 1/2, the height was 2, and the area was 1. And if I made the width of this thing, so if I shrunk the width of this down to, I don't know, 1/10, I would need the height to be 10 so that the area is still 1. And so in this case, if I wanted the width to be 1/10, I would need to go out 1/20th to the right, 1/20th to the left, and then the height would have to be 10. And so we're just looking to preserve it so that when I multiply the width times the height, we always get 1. And I want to take the limit as the width goes to 0, and therefore the height goes to infinity. But it needs to go to infinity in a very specific way, such that when these multiply together, I get 1. So basically, I want the height, well, notice, is to always be the reciprocal of the width, right? The height is 1 over the width. So that's how I want to think about this delta function. So one way we can kind of do this a little bit more formally is with the following notation. I'm going to call delta with a subscript, for now I'm going to just use an a, of, let's say, some value t. It's going to be equal to the following values. So we kind of already set up here, it has 2 values, either 0 or infinity, but I want to be a little bit more specific. So this delta with the subscript of a isn't quite the delta function yet. It can take on 3 values. It can take on 0, or 1 over 2a. And I'm picking it in this manner so that I can kind of follow what we just did here. Notice that the width of the graphs that we just did is can be thought of as basically 2 times whatever the x value is, right? When the width was 1/2, it corresponded to the 2 x coordinates, positive 1/4 and negative 1/4. When the total width was 1, it corresponded to the 2 endpoints of our interval being negative 1/2 and positive 1/2. So I'm going to basically scale that out in such a way that we don't need to worry about that. So it's going to be 0 for all the values of t basically less than some value a. And it's also going to be 0 for all the values of t greater than some value a. And then in between, it's going to be this height 1 over 2a. So for the values of t in between, t greater than a, t less than negative a. Let me clean this up. It'll make more sense. Negative a, positive a, and this one goes between the two. Negative a less than positive a. We have to assign equality to a somewhere because otherwise we're basically skipping that point. And the default way to do that is basically that we're going to let like this be, let's just say that's our less than or equal and that's less than or equal. So we'll have our equalities be on the left sides of each of these sort of little intervals. Let me put commas just for clarity. But the idea here is a more careful version of what we outlined above. Right? It's 0 away from the center, And here at the center of from what I'm calling now A, if I'm calling this point right here A, so in this case it was 1/4, here it was 1/2. I'm picking a value of A such that the total height of this thing isn't just 1 over A, it's 1 over 2A, because the total width, you'll recall, is 2A. So note here, the width is equal to 2A, and that's why I'm using 2A in the denominator here for our height, 1 over width. So we've got this function set up. You pick a value of A, and this thing will always integrate to 1. It's going to give us the pictures that we've got above. So here's a value where, or here's the picture if A is equal to 1/2. Here's the picture if A is equal to 1/4, and it always integrates to 1. What we want to do to get the actual delta function, so to get the Dirac delta function, and I should capitalize it, it's a proper name after a French guy named Dirac, the Dirac delta function, take a limit. Specifically, we're going to take the limit, so I'm going to write the delta of t is equal to the limit as a goes to 0 of delta sub a of t. So again, we're taking the limit as the width goes to 0, and that will automatically make the height go to infinity in the exact correct proportion that we're looking for. So this is the way that we're going to define it. It is equal to 0 basically everywhere away from t equals 0, and it's infinity at t equals 0, but in this specific way, we're approaching those 0, that specific 0 and that specific infinity using a limiting tool on this function right here. So that's what it's going to look like. I do want to just keep in mind that we can shift this function. So we can shift the Dirac delta function left or right as we did with the Heaviside function. And so different books have different notations for this. I'm going to avoid using a subscript here, but some books use a subscript here. I'm going to avoid using it because we've already used this subscript on our delta function to kind of refer to the basically the width, or half the width at least, of one of these pictures. So it doesn't make sense to use that as also for the shift. So what our book does is it uses t0. So just know that delta of t minus t0, for example, is the Dirac delta function. Centered at t0. So we can shift it. Again, the idea being that the Dirac delta function is infinity whenever its argument is 0. Now that argument will be 0 when I plug in t equals t0. So plug in that specific value of t, and that's where our spike will occur. So this is the notation our book will use, and I'll try to stick to similar notation to that. But just know there are some other books that instead they would use notation that looked like, maybe letter C down there, and this would be equivalent to the same notation that we used above with the Heaviside function. This type of notation also exists, but I will, I think, try to avoid doing that because that's not how our book does it. Okay, so we've got these two functions. I gave you the physical interpretation of the first one. We could think of it as an on-off switch. How can we think of the Dirac delta function? And I called it a delta function up here. That should be a delta. Let me rewrite that as well. Delta. Okay. So if this one up here is an on-off switch, if the Heaviside function is off and then we turn it on, the delta function can think of basically, or can be thought of as basically like hitting something with a hammer. the Dirac delta function can be thought of as hitting something with a hammer, like an instantaneous transfer of momentum. So hitting our mass spring system, for example. With a hammer. It's an instantaneous transfer of momentum. Okay, so there's kind of the interpretations. I want to talk about what the Laplace transforms of these things look like real briefly, at least mention them. They are in our tables, so we don't need to go into too much depth, as well as a couple of other little kind of helpful things that show up. So there's a couple of properties of these. In fact, let's just focus before we talk about the properties. Let's just talk about the Laplace transforms. Okay, so what do the Laplace transforms of these functions wind up looking like? So if we take the Laplace transform of our Heaviside function, uc of t, again, we can just go over to our table and see what that looks like. It's down here towards the bottom. So here's the Heaviside function, u sub c of t, which again is lowercase u parentheses t minus c, either notation, or again, capital U is totally fine. What we get out of this is e to the negative cs over s. That's what that Laplace transform looks like. And similarly, if we take the Laplace transform of the Dirac delta function, so I'll write it as whatever, t minus t naught to be preserve the notation that our book uses. The Dirac delta function's over on the other column, right here. So here's the notation they use here. They use c instead of t naught in this table, but that's totally fine. It gives us something actually quite similar. It gives us e to the negative, in this case, t naught s. So you can call it t0, you could call it c. I don't know if you prefer to keep the notation similar to what's in the table, or if you'd rather keep the notation similar to what our book uses, but you can kind of pick and choose which one makes more sense to you. I will mention that in both of these cases, there is an added restriction that s has to be greater than 0 in both of those cases. So this is what we've got. And there are some properties that we'll need as well. So here are the properties related to this. One of them is that basically if you have the Heaviside function multiplying another function, so if we take the Laplace transform of that, so this is the Heaviside function times another function, which is very often going to be the case. Often it'll show up like this. And you take the Laplace transform of that. So our Laplace transform of our Heaviside function, u sub c of t, times some other function, f of, and we'll have it shifted so that that function, f of t minus c, also has sort of its origin shifted to the same point as this. Basically, they're both functions centered at t equals c. But if we take the Laplace transform of that, you get the following. You get e to the negative cs, which isn't all that surprising. That's what showed up here, e to the negative cs, times the result of whatever you'd get if you just took the Laplace transform of f of t by itself. So basically what you get is e to the negative cs times our capital F of s. And we're going to definitely use that property. And again, that one shows up in here as well. It is right here, number 27. right? Here's the exact one that we just wrote down, but this is going to be a common one that we'll use. Similarly, if we're transforming sort of backwards, you could think of it as just obviously going in the reverse direction of this. So just keep that in mind as well. There's also one other property, and this second property is what's often referred to as a sifting property for the Dirac delta function. So of this bad boy. In fact, let me not even say delta of t. Let me be more general. Delta of t minus t naught. The idea is that if you integrate from a to b some function f of t times the delta function t minus t naught. If you think about what it means to multiply these two functions together, we know that this function's 0 basically everywhere, and then it's infinity exactly at t equals t naught. Whereas this function could be, any other function that we want to talk about. So what happens when you multiply them together? Well, definitely you're going to get a result that's 0 almost everywhere, but then it's going to have some value at t equals t naught that looks different, right? This part jumps to infinity at t equals t naught. What does this do? It's some finite value, presumably. And what you wind up with is, if you integrate through this, so if we complete that integration, all you wind up with is getting f of t0. So the idea is, like, imagine we just had our f of t be the constant function t, or f of t equals 1. Well, then we're getting exactly what we got up here in these pictures. If our function that we're multiplying our delta function by is just a constant 1, you're just going to get an integral of 1 out of the whole thing, right? The area is going to be 1. And what this is saying is, if you have some other function here, an exponential, a sine or a cosine, a polynomial, any function, and maybe it has a value of a height of 2. This function has a height of 2 at t equals t naught. Well, if you took it out, the whole thing would integrate to 1, but we're basically at that single point doubling the height, because this exactly at t equals t naught can be thought of as a constant of kind of 2 if it were doubling the height there. Or maybe f of t naught is 3, and then we're just tripling our Dirac delta function at that point, and so you would get that result out of it. So basically, the whole thing integrates to 1 times whatever the height of our function is at that specific point that we're evaluating the delta function at. So it's going to go to this, assuming, let me just mention that this assumes that a is less than or equal to t naught is less than or equal to b. That the value of t naught is, in fact, exists somewhere on the interval that we're integrating. If we're integrating between 0 and 1 and t naught is 3, then this function is 0 everywhere on that interval, and the whole thing will integrate to 0. But otherwise, it should integrate to this value, assuming t naught shows up somewhere on the interval. The spike, so to speak, is somewhere on the interval that we're integrating over. And that's just another really useful property that shows up quite frequently. So just keep those two things in mind. So the main takeaway that I want you to have from all of this really is, we can Laplace transform these discontinuous functions, because if we go back to the properties that we talked about way back in the first Laplace transform video, we didn't need our functions to be continuous. They were allowed to be discontinuous in order to apply a Laplace transform. And they just had to be, so they could be discontinuous as long as they were of exponential order. And that's the case with both of these functions. So they have Laplace transforms, and the important thing about them is their physical interpretation. The delta function, you can think of it as hitting our mass spring system with a hammer. The Heaviside function, you can think of it as flipping a switch that suddenly turns on some external force. Maybe there's an electromagnet that you hit the switch at whatever time 3, and suddenly that magnet's pulling on the mass downward, and it's going to clearly affect the behavior of our mass spring system. So I really want to think about these in the context of like a mass spring problem. And within that context, I want to do some examples. So one thing real quickly, let's just practice doing one like inverse Laplace transform, because that's really what we're going to wind up having to deal with. So let's do one example of just doing an inverse Laplace transform of some function I give you, and then we'll actually do one in the context of a differential equation. So I want to just find the inverse Laplace transform. Taking the Laplace transform is going to be pretty easy. It's the inverse transform that's always the difficult part, right? Doing the algebra to make this look like something that we can do an inverse transform of. So I want to find the inverse Laplace transform of a function that looks like this. It looks like e to the negative 2s over s squared plus s plus, no, let's do minus 2. Okay, so here's the function I want to deal with. What we want to do is basically whenever you see an exponential survive into your Laplace space, right? So it's an exponential of s. This is going to be a good indication that when you inverse transform back, you're going to be dealing with a Heaviside function. Notice that in both of these two functions, they involve basically e to the s, or e to the negative cs in this case, e to the negative t naught s in this case. But e to the s's indicate that we're dealing with one of these discontinuous functions. So let's take a look at exactly what goes on here. So what I want to do is basically factor out, whenever you see an exponential in your Laplace space, so basically in your functions that involve s, you basically always want to start by factoring that piece out. So I'm going to factor it out, and at the same time I also want to factor out the bottom. So let's look at our f of s. Our f of s in this case is going to be e to the negative 2s, I'll pull that piece out, times 1 over, I can factor this denominator as s, what, s minus 1 and s plus 2, s minus 1, s plus 2. Let me just double check. I'd get s squared plus 2s minus s. That gives me the plus 2 minus 1 gives me a coefficient of positive 1. And then the negative 1 times the 2 gives me the negative 2. So here's my factorization. And so if you want to, you can basically think of this as basically e to the negative 2s times some new function that I'll call capital G of s, because we've already used f. And the point being, there's nothing special about this g. If it weren't for this term sitting here, if this was gone, right? So if this was gone, we would just apply our normal approach to inverse transforming this, right? I would use partial fractions to separate this into two separate fractions that both take a form that I can inverse transform. But because of this piece, it complicates things. So I want to think about just this piece by itself. So this piece is what I'm calling our g of s term. So just keep that in mind. And actually, let me come back and erase my crossy-outy part. But that's what I'm calling g of s. It's basically just that piece. So I want to focus and pretend that this exponential weren't there for now, and let's just get g of s in a form that we could inverse transform it. So let's focus on that g of s. And keep in mind, basically what we're going to do is we'll use this transform right here, but again, I'm using g instead of f. So I'm going to switch the notation, but I'm going to use the fact that basically if I want to do the inverse Laplace transform of e to the negative cs times what I'm calling now capital G of s, right? Again, I'm just copying this notation right here, but switching the f to a g. That inverse transforms back to this. So this will become u sub c of t times, in this case, g of t minus c. So this is what I want to use. We're going to be using this setup. Remember, the inverse transform of our g of s will just go to this lowercase g. So if I can just figure out how to inverse transform the g of s term, this e to the negative cs term, all it tells me is that the resulting part will be multiplied by a Heaviside function that's shifted by a value c. And that will also have to shift the argument of whatever we get by inverse transforming our g of s, we'll have to shift the argument. It won't just be t, we'll have to shift the argument to be t minus c. So let's see what that looks like. So for now, let's just focus on g of s. Basically, so we need the inverse transform of just that g of s term to start with. Oops. Let's get my notation correct, do my curly brackets. There we go. So this is what I'm trying to focus on to start with. Okay, so what is that piece going to look like? Well, we do our normal math. We say, okay, let's do our partial fractions. I have 1 over s minus 1, s plus 2. I want to rewrite that using partial fractions. I'm going to get a over s minus 1 plus b over s plus 2. If we were to find a common denominator, we'd get a times s plus 2 over s minus 1 times s plus 2 plus the b over s plus 2 term gets multiplied top and bottom by s minus 1. Okay. After that, we compare just the numerators of these two equivalent results. So on the left, we have the 1. I'm comparing this numerator to this numerator. They're equivalent to each other, and the denominators are the same, so the numerators must also be the same. We've got a times s plus 2 plus b times s minus 1. This is an easy one. We have two distinct roots, so two linear factors for our roots. If I just plug in s equals -2, I'll get a lot of cleanup, and if I plug in s equals 1, I'll get a lot of cleanup. So when we plug in s equals -2, on the left I still have my 1. On the right, this term will go to 0, so I'll have 0a plus, plugging in a -2 here, I'll get -3b. That's what I get out of that one, plugging in a -2 for s. For the other one, I'll have 1 on the left, so I'm plugging in s equals 1. Here I'll get 3a, and over here I get 0b. And between the two of these, this one, top one tells me that b has to be equal to -1/3, and the bottom one tells me a has to be equal to +1/3. And so this can be rewritten. So we have that our g of s is really equal to, we can think of it as a 1/3 times 1 over s minus 1 minus 1/3 times 1 over s plus 2. S plus 2. And this is now ready to inverse transform because these two pieces, after we factor that constant out, those two pieces look exactly like here. Our expression that shows up in our second Laplace transform in this table over here, right? So 1 over s minus a. So in this case, a is equal to 1. In this case, a is equal to -2. And so when we Laplace transform this, so we're applying our inverse Laplace transform, we're going to get that g of t is equal to 1/3. This first one is e to the t, right? Because our value of a is 1, so we just get e to the 1 times t. And then for the second one, it's -1/3 e to the -2t, because again, for this one to work, a would have to be -2 to match these up. So we'd get e to the -2t. So there's what our g of t looks like. But remember, that's not our answer. Our answer is going to be this, because we have something that doesn't just look like the inverse transform of g of s, it's the inverse transform of this e to the -2s times g of s. So we use this property, which is number 27 in our table. And again, this is the second Laplace transform table, the shorter one. So I'm using this property. We have something of this form. It needs to turn back into this. And that's exactly what I have written down right here. So what we ultimately get, the following. We are going to get that our f of t, which is the Laplace, the inverse transform of the original f of s. So let's write that. the inverse Laplace transform of the original f of s, which I'm going to call lowercase f of t. That lowercase f of t is going to be the Heaviside function, right, uc of t times our, what we're calling g of t minus c. Basically getting this argument right here. But what is our value of c that we're doing? What was our shift in this case? Well, I need to come back up and compare. We're comparing it to, so here's the two values, e to the negative cs. What value of exponential did we have? We had e to the negative 2s. So for us, c is equal to 2 if I compare these. So this is going to be the Heaviside function shifted to the point 2. And then we also have to shift the argument of our g of t function by 2. So c is equal to 2 for us. And so we wind up getting u sub 2 of t times our g of t with the argument shifted by 2. So every t needs to be replaced with t minus 2 that shows up here. So it's that times 1/3 e to the t minus 2 minus 1/3 e to the negative 2 times t minus 2. We want to put that in both places. So basically, I took the g of t that we found, and everywhere that t showed up, I replaced it with t minus c, where c was equal to 2. So I replaced them with t minus 2's. And then the whole result is multiplied by a Heaviside function, u sub 2 of t. And it all is due to this one particular form right here. This is where it all came from. So we'll get some more practice doing this on the next example. Let's do one that actually involves a differential equation. But essentially the idea is this result is going to be the result of, we'll get stuff that looks like this with an exponential in our S space whenever the original function has either a Heaviside function or a delta function in it. So let's look at another example. Let's do y double prime plus 2y prime plus 3y is equal to the sine of t plus delta of t minus 3 pi. And let's say that maybe y of 0 is equal to 1 and y prime of 0 is equal to 0. So there's my initial conditions. So there's a lot going on here. We've got presumably a mass spring system over here. There's a forcing term of a sine, so we have some harmonic forcing being applied. And then at time t equals 3 pi, we're basically hitting the whole thing with a hammer and changing what the forcing looks like. And that will affect the behavior from all time starting at 3 pi onward. We have given it an initial displacement, but no initial velocity. So that's the picture that we're looking at right now. So let's apply our Laplace transform and see what we get. So remember, when we hit the Laplace transform on y double prime, hopefully this is becoming second nature at this point, we'll get s squared times our capital Y of s minus s times y of 0 minus y prime of 0. So there is the y double prime term. To that, I need to add 2 times the y prime term. The y prime term is s times the capital Y minus y of 0. And then plus 3 of the original y, which transforms to just capital Y of s. So there's the whole left-hand side of our equation transformed. Now let's transform the right-hand side. When we hit the sine function, we can come over here to our table. And again, if you don't have these memorized, they're all in the table as well. They're down here. 35 and 36 were the ones that I just used. But now we're doing sine of t. If we go up here, sine of t will just be 1 over s squared plus 1. So 1 over s squared plus 1. There's our transform of sine of t. And then the last piece that we need is we need to transform this delta function. And so if we come back down to where the delta function shows up, it's in the second column. Here it is. We're simply going to get e to the negative cs, where c is whatever shift that we've just done. So in this case, our value of c is 3 pi. So from this, we're going to get plus e to the negative 3 pi s. So that's what this whole thing transforms to. So there's our result after applying the Laplace transform to the whole thing. Let's group the capital Y's together, factor them out, and then clean up the remaining terms, see what survives, and do a little bit of algebra and some partial fractions and see if we can solve this thing. So the next step is we get our capital Y of s. It's going to be multiplied, in this case, by s squared plus 2s plus 3. I know that. It'll always match the form of the characteristic equation that we have up here. So I've taken care of this term, and this term. This term we know because that initial condition is 0. Let's just mark it as 0 right now. We don't need to worry about that. So on the left, these are the only other, this one here and this one here are the other two terms that survive. So I'm going to have minus s times y naught, but what was y naught? It was 1. So minus s times 1, here's that minus s times 1, and then over here we're going to have a plus 2 times a negative y naught, but again that was a 1. So this will, when I multiply them together, get a minus 2 out of that. And we're left with on the other side, again I haven't touched those yet, s squared plus 1 plus e to the negative 3 pi s. Okay, so everything's gotten cleaned up. If we want to start keeping track of what's doing what, we can think of, again, the sine function. Here's our squiggly, here's our dashed, here's our triple underlined term, and this term doesn't contribute anything because it was 0, but we can now keep track of what effect each of those had. So here's our triple underlined terms. They showed up there and there. Here's our squiggly term, and here's our dashed line term. So just keeping all of these where they go. So we're going to move these guys over to the other side. Y of s times our big mess is equal to, we've got our 1 over s squared plus 1. We've got plus e to the negative 3 pi s. And moving those terms over, we've got a plus s plus 2 over here. And so now there's our squiggly, our dashed, and our triple underlined terms. So there's all our terms. This is what we've got. Last step, divide out by our quadratic here. And we will get, if we want to do it, let's just do it all here. So this first term will look like 1 over, we'll have s squared plus 1, s squared plus 2s plus 3. So there's that first term. The next term will look like e to the negative 3 pi s times 1 over the s squared plus 2s plus 3 term. And the last one will look like s plus 2 in the numerator over s squared plus 2s plus 3. And again, this one corresponds to our squiggly, our dashed, and our triple underlined if we're keeping track of which ones we're dealing with. So let's deal with each one of these individually and inverse transform them back. So we've got to change their form into something that shows up over here in the table. That's going to require some partial fractions and a little bit of algebra and so on and so forth. If we want to, we could also, I guess we can deal with this momentarily. We're going to have to factor this or complete the square if it's not factorable. We'll deal with that in a minute, and we'll get these things looking a little bit better. So let's start with our squiggly one. So let's start by looking at our squiggly term. Okay, so the squiggly term looks like this. We want to find the inverse Laplace transform of it. Okay, so let's start off writing it out. We've got this big ugly mess. I'll think of this as, again, our s squared plus 1 squared if we want for now. But what is this piece going to look like? How do we break that up? Well, we can't factor it because it turns out to be complex. So instead, we're going to take this term and try to rewrite it by completing the square. So I can complete the square on this one. It's going to be like an s plus 1 squared would give me those first two terms. So let me do it like this. S plus 1 squared. S plus 1 squared would give me s squared plus 2s plus 1. But I don't have s squared plus 2s plus 1. I have s squared plus 2s plus 3. So that means I have an extra 2 hanging out. And I'll write that as a root 2 squared just to preserve the format of everything that we're interested in. So here's a slightly nicer, well, it looks worse, but a more convenient way of rewriting what we've got here. Now we just need to basically figure out how to do our partial fractions on this. So this is going to be where it gets a little bit ugly. So I can't reduce this piece, right? It's a quadratic one that I can't simplify anymore. This piece is also a quadratic one I can't simplify anymore. So let's split them up as the two separate denominators. So one denominator is going to be s squared plus 1 squared, if you want to think about it like that. The other one's going to be the s plus 1 squared plus the square root of 2 squared. And they both require linear numerators. Over here, I want to think about it as a times s plus 1 times b. Because s over s squared plus 1 is going to easily convert, and I can have a just be the coefficient in front. And similarly, 1 over s squared plus 1 squared is going to convert very easily, and I can just have b be the coefficient out front. Over here, instead of just naively doing cs plus d, what I'm going to do instead is I'm going to do c times s plus 1 plus root 2 times d for the very same reason. Because if I look in my table at lines number 20 and or 19, those are the ones I'm going for here. So 20, for example, I want what appears in the numerator to match what's in parentheses. This s minus a and the numerator needs to match the s minus a down here. So because I have an s plus 1 here, I need an s plus 1 up here as well. And so I'm going to force factor that out ahead of time. And that way when I find c, it can just be pulled out as a coefficient sitting in front of the whole thing. Similarly, looking at 19, I don't want to just have a 1 in the numerator. So if I found d and pulled that out front and just had a 1 sitting up here, that wouldn't work. I need a root 2. I need a number that matches the number that shows up here. So I forced it there, and we'll just figure out whatever d happens to be that could come out and be a coefficient in front of that. So try to do this cleverly. It will save you work down the line most of the time if you're wise about what you pick the form of your numerator to look like. Basically, if you have a shifted s down here, make your s that appears in the numerator to have that same shift. If you've got some number down here, right, if it's 9, then that can be written as 3 squared, and you'd want to force out a 3 up here so that it matches the form that appears right here. The same number that should appear here and here. So just keep that in mind. So this is what I've done. We want to, again, find our common denominator. We would do that by multiplying top and bottom. Let me just rewrite this here. This first term would look like as plus 1b, or I'll drop the 1 for now, as plus b over s squared plus 1 times our big ugly mess that we have over here, s plus 1 squared plus root 2 squared. So there's that term over itself. And then the other term, which looks like c times s plus 1 plus root 2 times d over s plus 1 squared plus root 2 squared. So just copy this term down. Now I need to multiply top and bottom by this s squared plus 1 term. Okay, now this denominator, to make it totally clear, this denominator and this denominator, again, make it totally clear, they match, and they match the denominator over here. So we're just going to compare the numerators to try to solve for those 4 values, a, b, and c. So on the left, I've got a 1, and on the right, I've got a big, ugly mess. I've got as plus b times s plus 1 squared plus root 2 squared. And over here, we've got c times s plus 1 plus root 2d times s squared plus 1. There's our big hideous mess of a numerator on the right-hand side. Okay, because both of the terms that we had here were basically complex roots that we had to complete the square to set this up, we couldn't factor it into nice linear terms, there aren't really convenient values of s that we can pick to plug in that'll dramatically simplify this equation. So instead, I'm going to go the route of just comparing all the different orders of s. And what we'll see out of this is if we're careful here, we're going to wind up with terms up to s cubed. And hopefully that's kind of obvious. I'll wind up with, like, for example, right here. Here's an s, but it's going to get multiplied by this s squared. So we'll have up to s cubed. So let's actually multiply these out. At this point, it's often helpful to, instead of doing what we're doing here, and just remember, we did this intentionally to get the denominator to look how we wanted it to. But it helps to go back to the original form. Remember, this that I have written here in the square brackets is really just s squared plus 2s plus 3. So that's what I want to essentially replace it with. This is really just s squared plus 2s plus 3. So let's do our multiplications to kind of foil this out, so to speak. So I'm going to take the first term here, the as term, and hit it on all three of those terms, and that will give me an as cubed term, a 2as squared term, and then a 3as term. So now I've hit this one with that, that, and that. Now let's do the b on each of those. So then we'll get plus bs squared plus 2bs plus 3b. And now I've hit all the terms that showed up here. We have all 6 terms from multiplying this binomial times this trinomial. Do the same thing over here. We don't have, in this case, they're both just binomials, essentially, if you want to think about it. So let's multiply these ones out. When I hit this guy times this guy, it's going to give me, you can think of this as a CS. Maybe it's going to be easier to do that. Let's write this as CS plus C plus our root 2D if we want. Now we're really doing the whole thing. Oops. This might make it a little easier to see, so let's do the CS times each of those, then the C times each of those, then this term times each of those. So we're going to get CS cubed, that's this term times this term. Now do C times the S squared plus root 2D S squared. And then lastly, we're going to hit the 1 on all of those and get a plus CS plus C plus root 2D. So there is our hideous equation. It looks like one big hideous equation with 4 unknowns, but encoded in it are 4 separate pieces of information. We're going to look separately at the order s cubed terms, the order s squared terms. Let me zoom in so I can write a little more clearly. S squared terms, the order s to the first power terms, and then the order s to the 0th power terms, or the constants. Okay. So let's start with these, the order s cubed terms. On the left side of our equation, let's make it so we can see the whole thing at once. On the left side of the equation, there is no s cubed. So we have 0 s cubes on the left-hand side, and that's equal to, on the right-hand side, we have as cubed plus cs cubed. Those are the 2 s cubed terms, so a plus c of them. Good. Let's write down all of them first before we try to do any solving. For the s squared terms, again on the left, there's none of them. But on the right, we have 2a of them plus b of them. So 2a of them plus b plus c of them plus root 2d of them. So there's that one. Then we'll look at the order s terms, so all of the s to the first power terms. We have this one. So again, on the left we have 0. On the right we have 3a plus 2b. So I've got this one, and this one, plus c. Okay? And for the very last ones, the constants, on the left we have 1. There's our constant. And on the right we have, here's our first non-constant, 3b, plus c plus root 2d. So there are all of our equations. And now we just need to do various substitutions to go ahead and solve these. So let's take a look and see what we can do with this mess. These things tend to look pretty daunting, but I want to tackle it kind of one variable at a time, or one equation at a time. So let's start with this one. This at least tells us that a and c are opposites. If they add up to 0, this one implies that c is equal to the opposite of a, or a is equal to the opposite of c. So let's say c is equal to negative a, wherever c shows up. And that means that I can then rewrite some of these other equations. So, for example, we can come down to this one and replace that c with a negative a. And that means that this equation can now be rewritten as 0 is equal to, we're going to have 3a plus a c, but c is equal to negative a. So 3a minus a is going to be 2a plus 2b. And if 2a plus 2b is equal to 0, that also tells me that b is equal to negative a, which tells me that a, so again, c is equal to negative a, b is equal to negative a, so that must mean that c and b are the same thing as well. So if c and b are the same number. And that's going to simplify down in, for example, this one. So we know that so far, b and c are the same thing, and a is the opposite of whatever those are. So let's come down here. This one I can rewrite as, so I'm going to replace, we can either replace them all with the negative a's, we could put in b's here, we could put c's, but let's convert these two to just be one variable. So let's just stick with b, since we're already there. We've got 3b, we already know that b and c are the same thing. So let's replace this with a b. B and c are the same, so we have 3b plus another b, so that's going to be 1 equals 4b plus the square root of 2 times d. And that gives us a relationship we can use there. We can also come up on this one now and dramatically simplify this one. This one looks like, let's pick a letter to stick to. I have an equation down here that it only involves b and d, so let's write this one only in terms of b and d as well. That might make life a little bit easier. So in this case, if we write this in terms of b and d, we've got, in this case, so b plus c, but b and c are the same thing. So here's 2b plus 2a, but remember, a is the opposite of both b and c. So what I really have is basically a, which is the opposite of b. So I have negative 2b plus 2b. Really, when I add all these up, I get 0 plus root 2d equals 0. But that's really just root 2d equals 0. But that tells me that d itself has to be equal to 0. And now that I have that d is equal to 0, we can come back down here, and this equation is then simply 1 is equal to 4b, which means b is a fourth, which means c is a fourth, right? That means a is negative 1/4, and up here c is back to a 1/4. So you kind of just go back and forth, trying to eliminate variables as much as possible as you go. Stick to 1 or 2 variables that you're going to keep and try to eliminate the others. So just be consistent and maybe pick, I always want to try to, if it's possible, get rid of A, rewrite it as B. Or if it's possible, get rid of C and rewrite it as B. Whenever you can do that, try to stick to one letter or the fewest number of letters that you're trying to write in each expression. And if you do that, just kind of going back and forth through it, it may take a while, but you'll get there eventually. So after all of that, we get that the expression that we're trying to rewrite, the 1 over the s squared plus 1, I hope I've got this memorized correctly, s plus 1 squared plus root 2 squared term, that whole mess can now be rewritten as, look at it all on the screen at once, come on. It can be rewritten in this form right here with the values of a, b, c, and d that we just picked out. So the a value is going to be multiplied by s over s squared plus 1, and a was negative 1/4. So we get negative 1/4, whoa. So negative 1/4, come on, negative 1/4 times s over s squared plus 1, so there's one of them, plus a 1/4 times the b term was just 1 over s squared plus 1, plus 1/4 times the last one, which was the c over c times s plus 1. So it was s plus 1 over s plus 1 squared plus root 2 squared. And the last one was 0, so we don't need that last term. These can all be inverse transform. So if we apply the inverse transform, we get from these sets of pieces here, this one looks like a cosine. So let's go back up and just make sure we're on the same page here. Looks exactly like this expression right here with a equal to 1. So that's just cosine of t. So we've got a negative 1/4 cosine of t, a positive 1/4 times a sine of t. Right, this one looks like a sine function right here with a equals 1. And then the last one looks like a shifted cosine function. So a shifted cosine function means one of the exponentials times cosine. Here we go. Right here, that is number 20. So a shifted s over that same shifted s squared plus some constant squared. And so in this case, we've got our plus 1/4. The shift, we're shifting a plus 1 here. It's supposed to be a minus a, so our a must be negative 1. So that's e to the negative t. And we wind up with a cosine of root 2t. There's our cosine of root 2t term as well, because our value of b is the square root of 2. So here's the result of that one piece. Unfortunately, looking back at it, that's the one piece that we've dealt with. We still have to deal with these other two pieces, so let's focus on one of them now. Let's hit this one. So now let's look at the dashed line one. So now we're going to look at the dashed line one. It looked like e to the negative 3 pi s times 1 over s squared plus 2s plus 3. We've already factored this or completed the square on this denominator, so I know that this looks like e to the negative 3 pi s times 1 over, that was s plus 1 squared plus root 2 squared. So we're close to what we need to do, but what I need instead is I need a root 2 up here. If this was a root 2 up here, we'd be in good shape. So I'm going to force a root 2 up there. So let's change that to a root 2, but basically I've just multiplied the whole thing by root 2, so that means I need to divide by root 2 outside somewhere. This is now something that we can transform. We just did a transform very similar to this. It's going to look like what we have right here, but with a sine instead of a cosine. And what do we do when we have this e to the negative 3 pi s sitting out in front of things? Well, remember, whenever you have an e term sitting out in front of whatever the function is you're dealing with, it's going to transform backwards in this manner. It's going to yield a Heaviside function with a shifted version of whatever f transformed to. So keep this in mind. This is the one that we're looking at right now. Essentially, we want to apply this formula that says the inverse Laplace transform of e to the negative cs times f of s, which is what we're looking at right here. Here's our e to the negative cs. This is our f of s, and we just have a constant pulled out in front of the whole thing. But that's equal to u sub c of t times f of t minus c. So as long as we can figure out how to transform this piece back, our result will just look like a Heaviside function times the transformed version of this, where we just replace all the arguments with t minus c. So for us, the value of c for us is 3 pi. Right? Here's our e to the negative cs, e to the negative cs, so that means our c is equal to 3 pi. So what does this piece transform back to? Well, it appears exactly as line number 19. So we get from all of this, we're going to have a 1 over root 2, right? That's this constant that I'm going to pull out in front. We know that this e to the negative 3 pi s is going to yield a e sub 3 pi of t. Right? Here's our Heaviside function, shifted with the value of c equals 3 pi. And now we're just going to have to do the inverse transform of this. So I've taken care of the constant out in front. I've taken care of this piece. Now what is our f of t if this is our capital F of s? Well, again, looking at our table, that's going to be e to the at sine of bt, where our b value is square root of 2, and our a value is negative 1. So we're going to get e to the negative t sine of the root 2 of t. But now all I need to remember is this is f of t. Right? This would be f of t. We don't want f of t, we want f of t minus c. So everywhere t shows up in here, I need to replace it with a t minus 3 pi. So let's go back and replace all the t's that just showed up with a t minus 3 pi. So we have negative t minus 3 pi, and then we have sine of root 2t, but it's t minus 3 pi. And so this is the result that we get from that one term. So this is the result that we get from the from the dashed line term. So there's that piece of our solution. So we have two of the three pieces. We have this piece from the squiggly part. We have this piece from the dashed line. We just need now going back, a lot of work here. We now need the triple underline term. So we've done this one and this one so far. Let's do this one. So the last one is going to be, let me just put bullet points on these so they're easier to find when we're looking big picture. Let's find the last one. So let's look at the triple underline term. That term was s plus 2, s minus 2. I can't remember what it was in the numerator. S plus 2, I think. Yes, s plus 2 over the same denominator that we just have been dealing with. So s plus 2 over s squared plus 2s plus 3. So the nice thing is once you do the work once, you're going to deal with that same thing over and over again. That's the same denominator we've already dealt with. So we can rewrite this as basically s plus 2 over our completed square version on the bottom. So s plus 1 squared plus root 2 squared. And same thing, I can just split this up into two separate pieces. But I don't want s on top. I want s plus 1 on top. So I'm going to basically force this. We don't have to complete the square on this or anything. We can just do a little bit of algebra. I've already got an s plus 2. I'm going to break off an s plus 1 from that and have the s plus 1 over s plus 1 squared plus root 2 squared. That's almost there. Right? I've accounted for everything in the numerator except for an extra value of 1. So plus another 1 over s plus 1 squared plus root 2 squared. And now I've accounted for both of the constants. Basically, I split the, oh, come on, where's my mouse? Why is it not showing up? Come on now. Okay, my mouse has disappeared. Nope. Let's undo. There it is. Okay, it's back. Okay, long story short, I've accounted for the plus 2 by splitting it into a plus 1 plus another 1. This piece is ready to transform. This one, I need to do the same trick we just did a minute ago. I'm going to write this as a root 2, and then write a 1 over root 2 out in front of everything to account for that. And now those are both ready to inverse transform, so we're going to apply our inverse Laplace transform, and we're going to get that first term is just going to be, we just did it, it was e to the negative t cosine of root 2t. So that's what this one's going to go, and it just has a coefficient of 1 because this had a coefficient of 1. And then plus 1 over root 2 times what does this one inverse transform to? That was also one that we just did. It was e to the negative t times the sine of root 2 times t. So again, lines 19 and 20 in our table are the ones that I just used. So we've now got all the pieces that we need, and we can put together our full solution. So putting all of these together, we get out of the whole thing, so it's going to be the value of y of t that we were looking for. So coming back way to the beginning of the equation, our goal was to solve for y here, and it's going to be those three pieces. So the first piece is right here. The second piece is right here. And the third piece is right here. So we just need to add those all up. And we'll have the whole thing. So we've got, see if I can get it all on one screen here, negative 1/4 cosine of t plus 1/4, oh, come on now, plus 1/4 sine of t plus 1/4 e to the negative t cosine of root 2t plus 1 over root 2 times our Heaviside function u3 pi of t times e to the negative t minus 3 pi sine of root 2 times t minus 3 pi plus e to the negative t cosine of root 2t plus 1 over root 2 e to the negative t sine of root 2t. There's our answer. Obviously, some of these terms can be combined. So for example, this term that shows up right here is of the same form as this term right here, and I could combine those two pieces together to clean it up at least a little bit. But let's just keep track of where everything came from. These terms were our squiggly terms. This term was our dash term, and these two terms came from our triple underline. And so if we go back to the original phrasing of the problem and think about where those components came from, right? This sine of t led to the whole squiggly part down there at the bottom. The delta function, so we hit it with a hammer at time t equals 3 pi, and that changed the solution for all time after 3 pi. The initial displacement, that yielded the last term that's triple underlined down there. And so we can take a look at this result and know that if that initial condition had been 0, these terms would be gone. If we hadn't hit it with a hammer, this term would be gone. If we didn't have a sine of t as a forcing term on the right-hand side, these terms would be gone. And so that's kind of the idea that we're looking at when it's all said and done. We'd wind up with basically just a homogeneous solution, which would be, again, some combination of some of these pieces, but if our initial conditions are 0, even that homogeneous term, the constants would wind up being 0. So you can see each one of those pieces and kind of how everything is contributed from each term in the original problem. This is going to be, again, the only new wrinkle is getting used to doing this. So you'll have a couple of these on the homework. I'll put one on a quiz so you have a chance to practice it there. But basically, how do you deal with transforming and then inverse transforming Heaviside functions and Dirac delta functions? And it's always going to be the same procedure that we did right here in this one problem. So hopefully these, again, they look terrible. It's one long problem. Basically, if I gave you an exam, the whole exam could basically be this one single problem almost. Or maybe this is a good take-home problem on an exam or something like that. But these do get very hairy. They can be very long problems. So just keep that in mind. It kind of limits how hard and how long of problems I can give you on a timed exam. So don't sweat too much if these are taking you a while. They take me a while too. So good luck. Let me know if you have any questions about this.